In this class, I am going to discuss about the questions and the answers of the first mock test held on today, 16th May 2022. The question paper was made on the topic modern physics, actually on the non-electronics portion of modern physics. There were 30 questions and the time allotted for your answer was 30 minutes. Let us try to discuss the answers to which will help you to solve your question papers easily and to manage the time. So let us take the first question now. First question is that when the EM radiations of frequencies 4 into 10 to the power 15 Hz and 6 into 10 to the power 15 Hz fall on the same metal in different experiments, the ratio of maximum kinetic energy of the electrons liberated is 1:3. The threshold frequency of the metal is. Let us give the mathematical analysis from which we know that the incident radiation H nu energy of the incident radiation used in two ways. Number one, a portion is used to actually used as a work function and the rest portion is as the kinetic energy. So for the first frequency of radiation, we may write down that 4 into 10 to the power 15, that is the frequency, into H equals to phi 0 plus E, where phi 0 is the work function of the metal. For the second case, similarly we can write down 6 into 10 to the power 5 into H, 6 into 10 to the power 15 rather, into H equals to phi 0 plus 3 times kinetic energy 3. What to do? We are to calculate the threshold frequency of the metal. So in order to calculate the threshold frequency, we should actually multiply the equation 1 by 3, which will give us 3 phi 0 plus 3e equals to 12 into 10 to the power 5h. So this is equation number 2, this is equation number 3. 3 minus 2, equation 3 minus 2 gives us 2 phi 0 equals to 6 into 10 to the power 15 into h. So phi 0 equals to 3 into 10 to the power 15 into h. What do you need? You need to calculate the threshold frequency. So the corresponding frequency is phi 0 by h equals to 3 into 10 to the power 15 Hz. So our correct answer is 3 into 10 to the power 15. So the correct option is C. So the correct answer of the question number 1 is C. Next question. In the question number 2, we see that an ultraviolet light of wavelength 2000 angstrom irradiates a photocell made of molybdenum metal. If the stopping potential is minus 1.5 volt, what is the work function of the metal? So the energy of the corresponding radiation of 2000 angstrom is equals to 12.42 by 2 electron volt, that is your 6.21 eV, and the stopping potential is minus 1.5 volt. So the maximum kinetic energy of the photoelectron is 1.5 volt, 1.5 volt. So what is that? What is the work function of the metal? Work function of the metal, incident energy is 6.21 volt. A portion is used as a work function and the rest of the energy is used as the kinetic energy of the electron, that is 1.5 volt. So phi 0 equals to difference in between the two, that is your 1, 5, 7, 12 to 4.71 electron volt. You are to calculate it in joule. All the options are given in joule unit. So that is equals to 4.71. All you know that 1 electron volt equals to 1.6 into 10 to the power minus 19 joule. So that is your nearly 16 7.5 into 10 to the power minus 19 joule. 7.536, the multiplication gives you 7.536 into 10 to the power minus 19 joule. So the correct answer is C. So the answer of the question number 2 is C. Now let us take the third question. What does it say? The de Broglie wavelength and kinetic energy of a particle is 2000 angstrom and 1 electron volt respectively. If the kinetic energy becomes 1 MeV, then the de Broglie wavelength becomes. Now we know the expression for it, lambda, de Broglie wavelength, equals to h by mv. And when we are expressing this expression in terms of kinetic energy, that is lambda equals to h by 2me. So lambda is proportional to h by, or lambda is proportional to 1 by root e. Now the energy of the particle was 1 electron volt. Now it is 1 MeV. So the energy is 10 to the power 6 times. Root over of 10 to the power 6 is 10 to the power 3. So the wavelength is 10 to the power 3 portion of it. So the first time the wavelength was 2000 angstrom. Now the wavelength is 2000 by 1000. That is your 2 angstroms would be the answer. So the answer is 2 angstrom. So the correct answer is C. So the answer to the question number 3 is C. Now let us switch over to the fourth question. What does it say? A 200 watts sodium street lamp emits yellow light of wavelength 0.6 micrometer. Assuming it to be 25% efficient in converting electrical energy to light, the number of photons of yellow light it emits per second. Street lamp having power 200 watt and 25% of energy is converting to light. So the corresponding light energy is 1/4, that is 50 watt or 50 joule per second. The number of photons of yellow light. So you are to calculate the number of photons. The energy carried by a photon is hc by lambda. If there are n number of photons, so the total energy carried is n hc by lambda equals to this 50 joule. Nh equals to 6.62 into 10 to the power minus 34 joule seconds is the velocity of light in vacuum, that is 3 into 10 to the power 8 meter per second, and lambda is here 0.6 micrometer. So 0.6 into 10 to the power minus 6 meter equals to 50. So n equals to what? 30 into 10 to the power minus 6. This is 19.86 into 10 to the power minus 26. That is your 10 to the power 20 into 1.5 nearly into 10 to the power 20. So the correct answer is A. So the correct answer to the question number 4 is A. Now let us see the fifth question now. Fifth question is that when the energy of incident radiation is increased by 20%, the kinetic energy of photoelectrons emitted from a metal surface increased from 0.5 electron volt to 0.8 electron volt, the work function of the metal. Mind that, so the 20% kinetic energy gives actually when the incident energy is increased by 20%, the kinetic energy of the photoelectrons changes from 0.5 electron volt to 0.8 electron volt. So the 20% of the incident energy E is actually 0.8 minus 0.5, that is your 0.3 electron volt. So the 100% energy, incident energy, is 5 times, that is 1.5 electron volt. 20% is 0.3 electron volt, so 100% is 1.5 electron volt, of which 0.5 eV is the kinetic energy of the photoelectrons. So the work function is the rest portion. maximum kinetic energy of the photoelectron is 0.5 eV. So phi 0, that is work function, is 1 eV. So the answer is B. So the answer to the question number 5 is B. Now let us see the question number 6. Let us consider the question number 6. The photoelectric surface illuminated successively by monochromatic light of wavelength lambda and lambda by 2. If the maximum kinetic energy of the emitted photoelectrons in the second case is 3 times that of the first case, the work function of the surface is. Now let us write down the Einstein equation first. All you know here, the Einstein equation is hc by lambda, that is the energy of the incident photon, equals to phi 0 plus maximum kinetic energy. In the second case, lambda should be replaced by lambda by 2. Hence, 2hc by lambda equals to phi 0, but the kinetic energy is 3 times, that is 3. So, we are to calculate the work function. So, what to do? We are to eliminate E. So, multiply the equation 3 first. Then 3 plus 3 phi 0 equals to 3hc by lambda. Difference of the equation 3 and 2 gives 2 phi 0 equals to hc by lambda. So phi 0 equals to hc by 2 lambda. So work function is hc by 2 lambda. Correct answer is 6c. Next question is question number 7. For the question number 7. Electrons of mass m with de Broglie wavelength lambda fall on the target of X-ray tube. The cutoff wavelength lambda 0 of the emitted X-ray. Electrons of mass m and de Broglie wavelength lambda. We know that lambda equals to h by mv. Fall on the target of X-ray tube. The cutoff wavelength lambda 0 of the X-ray. Cutoff wavelength lambda 0. All you know that hc by lambda 0 equals to E. That is the energy of the maximum energy of the electron. Mass m, electrons of mass m with de Broglie wavelength lambda fall on the target of X-ray tube, the cutoff wavelength. The maximum kinetic energy of the electron is converted into X-ray and to give you the minimum wavelength, that is the cutoff wavelength of the emitted X-ray. So, what to do? We are to transform this momentum to the kinetic energy of the electron. So, mv equals to root over 2me, hence lambda, de Broglie wavelength, lambda equals to h by twice me. Now, what to do? We have to equate the energy term. What is that? From the first equation, this is hc by lambda 0. From the second equation, E equals to what? hc by 2m into lambda square. Equate it. 2m into lambda square. The cutoff wavelength, you need lambda 0 equals to what? So, lambda 0 equals to 2mc lambda square by h. That is equal. Number A, 7A is the correct option. Let us go to the next question. That is the question number 8. Radiation of frequencies nu1 and nu2 made to fall in turn in a photosensitive surface. The stopping potential in the two cases is V1 and V2 respectively. The value of Planck's constant in terms of nu1, nu2, V1 and V2. When radiation of frequency nu1 falls on the metal surface, then from Einstein equation we know that h nu1 equals to phi 0 work function plus Emax, and Emax is measured in terms of stopping potential as EV1 for the first case. So h nu1 equals to phi 0 plus EV1 gives you the equation number 1. For the second case, h nu2 equals to phi 0 plus EV2. That's the equation number 2. Now what to do? You have to calculate the Planck's constant. So there is no phi 0 in the options. So we are to eliminate phi 0 from equation 1 and 2. So make the difference. Take the difference between equation 2 and equation 1, which gives you E into V2 minus V1 equals to H into nu 2 minus nu 1. So H equals to E into V2 minus V1 by nu 2 minus nu 1. So correct answer is C. So the correct option to the question number 8 is C. Next, question number 9. Let us see the question number 9. If K1 and K2 are the maximum kinetic energy of the photoelectrons emitted when light of wavelength lambda 1 and lambda 2 respectively incident on a metal surface, if lambda 1 equals to 5 lambda 2, then similar problem. We know that total energy E is used as two ways. First one as a work function, number two the kinetic energy of the photoelectrons. So for the first case, E equals to phi 0 plus K1. And for the second case, all you know that energy E equals to Hc by lambda. Here lambda 2 equals to lambda 1 by 5. So the energy in the second case is 5 times of the first one. So we may write down phi B equals to what? Phi 0 plus K2. Phi 0 plus K2. What is the options? What are the options there? Options give you the relation between K1 and K2. There is no phi 0. So to eliminate phi 0, first multiply the equation 1 by 5 and then make the difference between the two equations, equation 2 and the multiplied equation. That is phi b equals to 5 phi 0 plus 5 K1. This is equation number 3. If you get the difference between the two, 5e equals to 5e equals to phi 0 plus K2. From the first equation, we may also write down that and you may equate it. So 5 phi 0 plus 5 K1, that is 5e, means 5 phi 0 plus 5 K1 equals to what? Phi 0 plus K2. So K2 equals to what? 5 K1 plus 4 phi 0. So K2 is greater than 5 K1. K2 is greater than 5 K1. So K2 is greater than 5 K1. So B is the correct option. So the correct option to the question number 9 is B. Now let us see the question number 10. Let us consider the question number 10. When a monochromatic point source of light at a distance 0.2 meter from a photoelectric cell, the cut-off voltage and the saturation current are respectively 0.6 volt and 18 milliampere. If the same source is placed at 0.6 meter from the photoelectric cell, then all you know that the stopping potential is independent of the source distance from the cell. So if the stopping potential for the first case is 0.6 volt, for stopping potential also in the second case is 0.6 volt. But photoelectric current I is proportional to the incident light intensity or intensity of the incident light. And intensity of the incident light is proportional to 1 by d square. Actually, it follows the inverse square law. In the first case, the distance was 0.2 meter. The distance of the point source from the metal surface or photoelectric cell is 0.2 meter. But in the second case, it is 0.6 meter. So the distance is 3 times. Hence the intensity will be 1 by 9 times. 1 by 9 times. Intensity in the first case, if it were I, then it was in the second case is I by 9. So the photoelectric current will be 1 by 9 times the 18 milliampere into 1 by 9, that is 2 milliampere. So in the second case, photoelectric current should be 2 milliampere. So we have find that the stopping potential in this case is 0.6 volt, as well as the saturation current is 2 milliampere. From the options, we find that B and C are the correct option here. So the actually correct option is D, which reveals that both B and C are correct. So the correct answer to the question number 10 is D. Now let us switch over to the next question. A beam of cathode rays is subjected to crossed electric field and magnetic field. The fields are adjusted such that the beam is not deflected. The specific charge of the cathode rays is given by, you are to express the specific charge of the cathode rays. So what to do? There is no deflection of the stream of charged particle. Force given by the or provided by the electric field is small e into capital E equals to force provided by the magnetic field, that is your BE into V. Small e being cancelled out, so capital E equals to B into V. This is the first condition. The fields are adjusted such that the beam is not deflected. The specific charge of the cathode ray. If a cathode ray specific charge required, you are to record E by M, as they are accelerated by a potential difference V. So the energy acquired by cathode ray is EV equals to half mv square, energy of the electrons, corresponding electrons. So we have to express small v from the second equation and put it in the first equation. So v square equals to 2ev by m. So v equals to, or v square, you may put it there in such a way, e square equals to b square v square. So if you put v square equals to 2ev by m, this is equals to b square into 2ev by m equals to e square. We need to find E by m, that is the specific charge, equals to E square by 2b square into V. E square by 2b square into V. So D is the correct option. Answer to the question number 11 is D. Now let us see the question number 12. The electron in the hydrogen atom. In the question number 12, we see that electron in the hydrogen atom jumps from excited state n equals to 3 to the ground state, and photons thus emitted irradiate a photosensitive material. If the work function of the material is 5.1 electron volt, the stopping potential is estimated to be. Then let us see the energy of the electron in the third orbit as well as in the first orbit. In the nth orbit, energy En equals to minus 13.6 by n square electron volt. So for the third orbit, it is minus 13.6 by 3 square, that is your minus 1.51 electron volt. And for the first orbit, it is minus 13.6 electron volt. So the energy difference, because the excited electron goes to the ground state, so it will emit the energy difference between the two orbits, and the energy difference is E3 minus E1 equals to, in fact, 1 minus 1.51 plus 13.6, that is equals to 12.09 EV. 12.09 EV. Now this energy is used in two ways. For the photoelectric emission, incident energy is used in two ways. First, a portion is used as a work function, that is 5.1 electron volt in the given problem, and rest portion is used as the kinetic energy of the photoelectrons. Maximum, if we write down Einstein equation, that should be the maximum kinetic energy of the photoelectrons. So E max equals to difference between the two, that is your nearly 7 electron volt E max. 7 electron volt is the energy. So the stopping potential V0 is 7 volt nearly. So correct answer is D. So the correct answer to the question number 12 is D. Let us take the next question. Next question means the question number 13. In the question number 13, light of two different frequencies whose photon have energies 1 electron volt and 2.5 electron volt respectively illuminate a metal surface of work function 0.5 electron volt. A ratio of maximum speeds of the emitted electrons in the two cases. So, the kinetic energy of the electron in the first case is the difference in between the two energies, that is, first of all, the incident energy and the work function, that is 1 minus 0.5 equals to 0.5 electron volt. So, the energy in the second case, E max in the second case, should be the difference in between the two energies, that is 2.5 electron volt, difference 0.5 electron volt, that is 2 electron volt. In the first case, let the energy be E1, and in the second case, let the kinetic energy be E2. Then E1 by E2 equals to 1/4. E1 equals to half mv1 square and E2 equals to half mv2 square. If the velocity of the electrons in the two cases were v1 and v2 respectively, then half mv1 square by half mv2 square equals to 1/4. So v1 square by v2 square equals to 1/4. So v1 by v2 equals to half. So the required ratio is 1:2. So the correct answer is B. So the correct answer to the question number 13 is B. Let us take the question number 14. What does it say? Consider third orbit of helium He plus. Using non-relativistic approach, the speed of electron in the orbit will be. The speed of electron V equals to, we know that C by 137 into Z by N, where C is the velocity of light in vacuum. That is, the value of C is 3 into 10 to the power 8 by 137. For helium, value of Z is 2, and for the third orbit, N is 3. So this is 2/3. So this is equals to 200 by 137 into 10 to the power 6 equals to 1.63, 630, 1.4, 520, 548, 52, 82, 820, 1.46 into 10 to the power 6 meter per second. So the correct answer is D. Correct answer of the question number 14 is D. Now let us take the 15th question, number 15. In the question number 15, we see that an electron of mass m and a photon have same energy E. The ratio of de Broglie wavelength associated with them. Let us take the question at first. De Broglie wavelength and the energy E. All you know, lambda equals to h by mv. The Broglie wavelength, lambda equals to h by mv equals to h by root over 2me. We are expressing this wavelength in terms of energy of the electron. Energy of the photon is also E. So E equals to hc by lambda. Let the wavelength, the Broglie wavelength of the electron be lambda 1 and that of the photon be lambda 2. What to do? We have to find the ratio of the wavelengths. So lambda 2 equals to hc by E, then lambda 1 by lambda 2 gives you lambda 1 equals to h by root over 2me by lambda 2. So lambda 2 gives you E by hc equals to 1 by c into root over of E by 2m. So C is the correct option to the question number 15. So 15C is the correct answer. Now let us take the question number 16. An electron of mass m with an initial velocity v0i enters an electric field E equals to minus E0i at t equals to 0. If lambda 0 is its de Broglie wavelength initially, then the de Broglie wavelength at time t. So initial de Broglie wavelength lambda 0 equals to h by mv0. v0 being the initial velocity. Now, electrons are accelerated by the field, and as the charge of the electron is minus E, so the force provided by the field on the electron is E into E0. So the acceleration is E0 by m. So velocity of the electron at time t is v0 plus at. That is your v0 plus E0 by m into t. Now the corresponding de Broglie wavelength lambda equals to h by mv, that is your m into v0 plus E0 by m into t. We need mv0 actually. So h by mv0. Take v0 common from the bracketed quantity, then it is 1 plus E0 by mv0 into t. But we know that h by mv0 equals to lambda 0 from the first equation. So putting it there, we get lambda equals to lambda 0 by 1 plus E0 by mv0 into t. So the correct answer is lambda 0 by 1 plus E0 by mv0 into t. So correct answer of the question number 16 is A. Next, let us see the question number 17. In the question of 17, the electric potential between a proton and an electron is given by V equals to V0 ln R by R0. V equals to V0 ln R by R0. Where R0 is a constant, assuming Bohr's model to be applicable, write variation of Rn with n, where n being principal quantum number. Now, expression for potential is given. All we know that the force acting is given by the intensity expression. So let us first calculate the electrical intensity here. We know that the relation between electric intensity and electric potential is E equals to minus dV dr. Minus dV dr. And if we take the magnitude of E, then E equals to dV dr. Equals to V0 constant 1 by R0, that is your R0 by R into 1 by R0. So this is equals to V0 by R. So the force acting on the electron is E into E equals to E V0 by R, and it gives you the corresponding centrifugal force, centripetal force, that is your mv square by R. Hence E V0 equals to mv square, which reveals that V is independent of n. Now Bohr's quantum condition gives you mvr equals to nh by 2 pi. As V is independent of n, so R is proportional to n. So we require the relation between Rn and n. Actually Rn is proportional to n, so the correct option is A. So the correct answer to the question number 17 is A. Let us take the question number 18. Another question from Bohr's theory. Bohr's theory related question. This is also Bohr's theory related question. Suppose an electron attached towards the origin by a force k by r, where k is a constant and r is the distance of the electron from the origin. By applying Bohr's model to the system, the radius of the nth orbit of the electron found to be Rn, and the kinetic energy of the electron found to be Tn, which of the following is true? So the force acting on the electron is K by R, which is actually giving the electron the corresponding centripetal force. Hence, the centripetal force on the electron when its speed is v, it is revolving in an orbit of radius r, is mv square by r equals to k by r. Again mv square equals to k. So v equals to root over k by m and independent of n, or number of the orbit, or the main principal quantum number. It is independent of the principal quantum number. Again, Bohr's quantum condition gives mvr equals to nh by 2 pi. B is independent of n, so r is proportional to n. Now, kinetic energy of the electron, half mv square equals to k by 2, and this expression also reveals that kinetic energy is independent of n, but r is proportional to n. So kinetic energy Tn equals to half mv square equals to k by 2, which is independent of n, but the radius of the orbit is proportional to the principal quantum number of the corresponding orbit. So the correct option is B. So the correct option to the question number 18 is B. Now let us take the next question. That is the question number 19. In the question number 19, we see that it is a hydrogen spectrum related question. In hydrogen spectrum, the shortest wavelength of Balmer series is lambda. We know that the wavelength of the incident of the emitted radiation lambda is given by 1 by lambda equals to r into 1 by n1 square minus 1 by n2 square. For the shortest wavelength of the Balmer series, n1 equals to 2 and n2 should be infinity. So 1 by lambda equals to r into 1 by 2 square, that is your r by 4. The shortest wavelength in the bracket series. For the bracket series, we know that n1 equals to 4 and n2 tends to infinity. In that case, if the corresponding wavelength is lambda 1, from equation number 1, we can write down 1 by lambda 1 equals to r into 1 by 4 square minus 1 by infinity. So, 1 by lambda 1 equals to r by 16. So, from equation number 2 and 3, dividing equation 2 by equation 3, we get lambda 1 by lambda equals to r by 4 into 16 by r, that is your 4. So lambda 1 equals to 4 lambda. So correct option is B, question number 19 having the correct choice B. Let us see the question number 20. It is also hydrogen atom problem. An electron in a hydrogen atom makes a transition from n equals to n1 to n equals to n2. The time period of electron in the initial state is 8 times that in the final state. The possible values of n1 and n2. Let us first see how the time period depends on the principal quantum number n. That should be our first objective. So time period t, we know that it is equals to 2 pi r by v. 2 pi r by v, where r is the radius of the orbit. And from Bohr's theory, we know that r equals to 0.53 into n square by z angstrom. And v equals to c by 137 into z by n. So the ratio r by v is proportional to n cube. So t is proportional to n cube. Now, the problem says the time period of electron in the initial state is 8 times that of the final state. So time period in the initial state be n1 and that in the final state be t2, and T1 is 8 times T2, so the ratio is 8, equals to what? Equals to N1 cube by N2 cube. Then N1 by N2 equals to 2. So N1 is twice the N2. In the first option, N1 4, N2 2. So the condition is actually satisfied here. But in the other options, in the option B, N1 is 4 times of N2. Option C, N1 is 8 times of N2. And in the option D, we find that the N1 is actually 3 times N2. So the correct option is A. So the actual answer to the question number 20 is A. Let us take the question number 21 now. In the question number 21, hydrogen atom from excited state comes to the ground state by emitting a photon of wavelength lambda. If R be the Rydberg constant, the principal quantum number n of the excited state for the emitted radiation of hydrogen atom, we know the expression of wavelength 1 by lambda equals to R into hydrogen atom excited state comes to the ground state by emitting a photon. It were in the excited state to the ground state. For the ground state, N1 is 1, and for the excited state, let it be N. Excited state be N. What to calculate? The principal number of the excited state. So we are to calculate N from here actually. So 1 by lambda R equals to 1 minus 1 by N square. Hence 1 by N square equals to 1 minus 1 by lambda R equals to lambda R minus 1 by lambda R. So N equals to root over of lambda R by lambda R minus 1. So the correct answer is A. So the correct option of the question number 21 is A. Now let us see the question number 22. At any instant, the ratio of the amount of radioactive substances is 2:1. Let the first substance and the number of atoms in the first substance be 2n0, then that in the second substance is n0. Their half-lives are 12 and 16 hours. The first one having half-life 12 hours, second one having half-life 16 hours. Then after 2 days, in 2 days there are 48 hours. What will be the ratio of the substances? Actually, the ratio of the substances means the ratio of the number of non-disintegrated atoms. In 48 hours, there are 4 half-lives of the first sample, and the second sample having 3 half-lives. We know that non-disintegrated atom after 4 half-lives is half to the power 4. So the number of non-disintegrated atom is, in this case, is 2n0 into half to the power 4. And in the second case, in the similar way, we can get the number of non-disintegrated atom is n0 into half to the power 3. So the ratio of the substances now is 2n0 into half to the power 4 is 2n0 into half to the power 3. 2n0 into 1/16 is 2n0 into 1 by 8. That is, your n0 by 8 is to n0 by 8. That is 1:1. The correct option to the question number 22 is A. Now, let us see the next question. Question number 23. In the reaction represented by Zxa 2, Z minus 2, Ya minus 4, 2, Z minus 2, Ya minus 4, 2, K, Z minus 1, A minus 4, the decay in the sequence is. Suppose in the first case, the change is the atomic number is 2 and that of the mass number is 4. So alpha particle is emitted in the first case. So the option either A or D is the correct one. In the second case, there is no change in the atomic number or mass number. second transition. So that should be the gamma radiation. For gamma radiation, electromagnetic radiation is emitted, but there is no change in either atomic number or mass number. In the third case, there is no change in the mass number, but atomic number is increased by 1 unit, that is beta ray is emitted. So the third emission is beta emission. So the correct option is D. So correct option to the question number 23 is D. Now let us see that question number 24. It is also radioactivity related question. The question says the half-life of radon is 3.8 days. After how many days will only 1/20th of the radon sample left over? 1/20th. 1/20th. Suppose half to the power 4 equals to 1/16th and half to the power 5 equals to 1/32. 120 is in between them. 1/16 is greater than T, 1/20 is greater than 1/32. So 1/2 to the power 5 is less than T is less than 1/4 to the power 5. So our given time, that is 1/20th, is in between 4 and 5 half-lives. 4 half-lives gives you, one half-life is actually 3.8 days, 4 half-lives gives you 3.8 into 4, that is 15.2 days, and 3.8 into 5 half-lives gives 19 days. So the answer should be in between 15.2 to 19 days. There is only one option left within that range, that is more than 15.2 days but less than 19 days, and that is 17. So the correct option to the question number 24 is D. Now let us see the question number 25. From question number 25, a nucleus with mass number 220 initially at rest breaks up, emits alpha particle. If the Q value, that is the total energy emitted in the reaction, is 5.5 MeV, the kinetic energy of the alpha particle. The corresponding decay is that some nucleus of value 220 gives you alpha particle, that is the nucleus of the helium atom, plus the rest nucleus having mass 216 unit. And correspondingly, as the momentum is constant, we know that E equals to P square by 2m. So the energy of each particle is proportional to 1 by m. So here E alpha by Ey is inversely proportional to the respective mass. So this should be mass of Y is 216 and mass of alpha is 4 unit, that is 54 by 1. So we have to calculate the kinetic energy of the alpha particle. And it is given that Q value of the reaction, that is total energy, is 5.5 MeV. So we are to find E alpha by E alpha plus Ey. E alpha plus Ey actually gives you the total energy, that is the Q value, equals to what? That is your 54 by 54 plus 1. Simple mathematical calculation gives you the ratio 54 by 55. E alpha. Q value is given here 5.5 MeV. Let us put 5.5 instead of E alpha plus Ey equals to 54 by 55. 10 times, so E alpha equals to 54 by 10, so E alpha equals to 5.4 MeV. So the correct answer is 5.4 MeV. So the answer to the question number 25 is D. Let us take the question number 26 now. It is also radioactivity related problem. A radioactive nucleus of mass number A and atomic number Z emits 3 alpha particles and 2 positrons. The ratio of the number of neutrons to that of protons in the final nucleus will be. দেখো প্রোটন আর নিউট্রনের proton and neutron ratio, you are to find the ratio of protons and neutrons. Let the first nucleus X having initial mass number A, atomic number Z, Zx emits 3 alpha particles. With the emission of 3 alpha particles, the nucleus Y having atomic number Z minus 6 and mass number A minus 12. Because in case of each alpha emission, there is a reduction of mass atomic number 2 and mass number 4 unit. So for the 3 alpha emission, there is a reduction of 6 atomic number and reduction of 12 mass number. And for 2 beta plus decay, that is your positron decay, actually there is no change in the mass number. But for each beta plus decay, you know that the atomic number increases by 1 unit. So for 2 beta decay, it decreases by 1 unit. For beta decay, actually beta plus decay, what happens then? Proton is transformed into neutron. Proton 1H1, neutron 0N1. So there is a change. Proton, that is, there is a decrease in the value of the atomic number. So for the 2 beta decay, there should be decrease in the number of atomic. There is a reduction of 2 in the atomic number. So the value should be Z minus 8. Now, proton exists, Z minus 8. Neutron exists, how many? Mass number minus atomic number, that is your A minus 12 minus Z minus 8. That is your A minus Z minus 4. A minus Z minus 4. So the neutron proton ratio is A minus Z minus 4 by Z minus 8. A minus Z minus 4 by Z minus 8. C is the correct option to the question number 26. Now consider the question number 27 now. The half-life of a radioactive substance is 30 minutes. The time taken between 40% decay and 85% decay. Disintegrated portion is 40%. So non-disintegrated portion is rest of the portion, that is 100 minus 40% is 60% in the first case. In the second case, 85% decaying says non-disintegrated portion is 100 minus 85%, that is your 15%. So in the first case, non-disintegrated atom was 60%. In the second case, it is 15%. So the ratio is 4. So N2 by N1 equals to 1/4, that is half to the power 2. So we have spent 2 half-lives. So T equals to time taken equals to 2T half, but tau half. 2 into T half, 2 into T half, half-life 30 minutes. তাহলে 2 into 30 minutes equals to 60 minutes. So D is the correct option to the question number 27. 27D is the correct answer. Let us go to the next question. It says, actually, what does it say? Hydrogen atom in the ground state is excited by radioactive radiation of 975 angstrom, number of spectral lines in the resulting spectrum. So the energy incident is 12.42 by 0.975. 12.42 by 0.975. The number equals to what? 12.4 by 0.98. 198, 262, 12 point something, 12 to 196, 640, 12.6, 588, 520, 12.6 EV actually, nearly. So the energy incident on the surface equals to what? The energy incident on the surface is nearly 12.6 electron volt. So 13.6 electron volt is the energy. Now 12.42 by 0.975, 12 point 12 point what this is, 12.1240 by 98, 42 actually, 12.42, 98, 262, 2, 196, 66, 0, 12.6, 7, nearly 12.7. So the energy is nearly 0.85 eV actually. That is the fourth orbit, because we know that En equals to minus 13.6 by n square, and 0.85 gives you equals to minus 13.6 by n square, so n equals to 4. So the number of spectral lines is 4C2, that is your factorial 4 by factorial 2 into factorial 2, that is 4 into 3 into factorial 2 by 2 into factorial 2. So 12 by 2 minus 6. So the number of spectral lines emitted is 6. So the correct option is B for the question number 28. Now let us take the question number 29. The following fusion reaction, here is a fusion reaction for us. What does it say? In the following fusion reaction, two deuteron atom nucleus actually gives you helium nucleus, a neutron, and 3.27 MeV energy. If 2 kg of deuteron is subjected to the above reaction, the energy released is used to light a 100-watt lamp. How long will the lamp glow? Now, mass of each deuteron is 1.67 into 10 to the power minus 27 kg for each proton. So the mass of each deuteron into 2. We are taking that the mass of each neutron and proton are equal. And for the reactant nucleus, there are 2 deuterons. So the reacting mass is actually twice this value. We are taking some approximation. Let us take 1.7 into 10 to the power minus 27 into 4. 6.8 into 10 to the power minus 27 kg. So how many reactions are possible? Reacting for one reaction, mass of the deuteron required is 6.8 into 10 to the power minus 27 kg. So there are how many such deuteron pairs in 2 kg? Let us see it. The number of deuterons pair in 2 kg is 2 by 6.8 into 10 to the power minus 27. And in each reaction, there is a liberation of nearly 3.27 MeV energy. So total energy emitted is 3.27 into 10 to the power minus 13 joule. And this energy released is used to light a 100-watt lamp. 100-watt lamp is using energy 100 joule per second, and it is using for let n second. Then we are to calculate n at first. Then n equals to what? 6.54 into 10 to the power minus 13 by 6.8 into 10 to the power minus 25. Here is another 1.6. 1.6 into 10 to the power minus 13 actually 1 eV equals to 1.6 into 10 to the power minus 19 joule. So 1 MeV equals to 1.6 into 10 to the power minus 13 joule. So this should be multiplied. 3.27 should be multiplied by 1.6 into 10 to the power minus 13. So there should be another 1.6. So the result is that 10.46 by 6.8 into 10 to the power 12 second. And in a year, we know that there are 3.15 into 10 to the power 7 second. So if we convert it into year, then we will find that the value we have to divide it by 3.15 into 10 to the power 7. Then what we get? 10.46 by 68 into 5, 340, 34, 102, 10, 204, 214 was 21.42 into 10 to the power 5, nearly 5.5 into 10 to the power 5. That is 5 into 10 to the power 4 years. 5 into 10 to the power 4 years. That is correct option is C. So the correct answer of the question number 29 is C. Let us take the last question. A radioactive sample emits n beta particles in the first 2 seconds and 0.5 n beta particles in the next 2 seconds. The mean life of the sample is. Let us take the number of decays dn1 dt equals to n1 into lambda. Similarly, dn2 dt in the second case, rate of decay equals to n2 into lambda. If we divide equation 1 by equation 2, then dn1 dt by dn2 dt, dn1 dt by dn2 dt equals to n1 by n2 equals to n1 was at first n1. A radioactive sample emits n beta particles, and in the next case it is 0.5 n. So the ratio is n by 0.5 n. That is your 2. So n1 by n2 equals to 2. So we spend a time period of 2 seconds, that is the half-life. Now we require mean life, T. We require mean life. So T equals to T half equals to 2 seconds. Because the number of non-disintegrated atoms in the second case is half the first one. N2 equals to what? N1 by 2. Now T average equals to what? TA into ln2. So T half equals to TA into ln2. So TA equals to T half means 2 by ln2. So the correct option to the question number 30 is C. So the correct option is C. That is the end of the discussion of the question paper. This is for the first time I am giving the answers in English. So I have made some mistakes. I expect your pardon from your part in this case. Now, the MCQ answer of the question paper is 1C, 2C, 3C, 4A, 5B, 6C, 7A, 8C, 9B, 10D, 11D, 12D, 13B, 14D, 15C, 16A, 17A, 18B, 19B, 20A, 21A, 22A, 23D, 24D, 25C, 26C, 27D, 28B, 29C, and 30C. And that is in the MCQ form. We expect to take two such examinations, two such mock tests in each week. And the next probable date of exam should be 20th May, 20th May, next probable date of exam. And that will be, the topic of that exam is modern physics, the total modern physics. So I suggest you to prepare yourself for the exam, for the coming mock test on total modern physics of your syllabus.